All right, velocity and other rates of change. We'll take a look at instantaneous rates of change. Our big topic that encompasses everything is motion or particle motion. Motion along a line, we'll look at change. The other thing that's a connection to this is derivatives in economics. If you're taking an economics course, so in other words, you're a person going into any kind of field where you have to take some kind of business courses in college, you'll have to take economics. It's all derivative stuff. There's tons of calculus in economics. So let's take a look at how to figure out motion. You have a copy of this function, which is listed on the screen. It got a little bit cut off here, but you can see what's happening with the function is what's happening along the line of motion is starting at S. S stands for position. So we're going to keep track of what's what. I reviewed this just briefly before those that were on the trip left. S stands for the position. So you're starting at position 0. So I want you to keep in mind where am I is my position. We're looking at a height. As you're looking at something in terms of a height in the position of the graph or the function, what's the maximum height it's going to reach? Notice what happens up here. It actually goes up, stops, and then comes back down due to what? Gravity. The velocity then when you're stopped and change direction is 0 at that point. So what's the time frame in this graph or this little timeline that we're showing here? That's what we're going to take a look at, is how to figure out the time, the velocity, acceleration, position, and so forth. What I'm going to do with these notes then is take you through an example and show you through the same example how to do each of the different processes of figuring out particle motion and what we need to know for calculus class. I have an example. I'm not sure if this is going to work, but I'll try it. It's called the monkey example because we'll see if it still works. What you can do with this is it'll show you exactly where the monkey, as you can see on here, it'll show you exactly where the monkey is trying to get the monkey to catch the banana, to eat the banana here. So you got a monkey, and this is what happens. Of course, it's due to gravity. So we can do throw above the monkey with gravity on, throw at the monkey at a fast speed with gravity on, throw at the monkey at a slow speed. And notice what the motion is, though, of this path. What's the motion? Is it going to go in a straight line? What do you think?
No.
No. What kind of function do you think this will be? Think about the motion of this. What will it end up being? Take a guess.
A parabola?
Yeah, parabola. Motion doesn't follow a straight line, everyone. It typically follows some kind of a curvature, and in this case, it typically follows some kind of a parabola. So let's see if any of this still hopefully works. Instantaneous rate of change. Notice that this is the same example and formula that we look at for derivative, because that is derivative. So derivative stands for instantaneous rate of change. In this case, we'll look at instantaneous velocity in our examples. It's the same formula that we use, so we call it the rate of change or instantaneous rate of change. Notice that in this case, we're still looking at a specific point, so A is in the problem rather than X. Again, with the problem, same as what we did before, I would get your derivative first. In this case, it'll be with T instead of X because we're looking at an actual time frame. And then plug in the number. This one is where we would plug in the number. So if I were looking at this problem again, I would probably just replace the A with an X. And then it's the same formula that we've been learning. Get the derivative. Once you have the derivative, then find the value for the derivative. Here's just an interesting example because it doesn't have to be something you typically think about when we're looking at instantaneous rate of change. Again, we'll do a ton with particle motion, but this is a little different example. Area of a square of radius A equals pi r squared. That's just a typical formula for the area of square of a function. Sorry, area of, not the area of a square, square of a function. So it's a typical area for a circle. Find the rate of change of the area with respect to the radius. Evaluate the rate of change. Anytime we're talking now about rate of change, we think about derivative. So we have the derivative of the pi r squared area is 2 pi r. This is one that's very unique in that the derivative is the circumference. It's the formula for circumference. So the rate of change when r equals 4, all we do is plug in the number. It doesn't matter what the concept is that we're looking at, whether it's particle motion or something else that we're looking at. We can always take the derivative anytime we're asked to find instantaneous rate of change or basic rate of change in this case, and then plug in the value. The only time where you don't take a derivative is where it says in the problem average rate of change. That's secant slope. Then we're back to the f of b minus f of a over b minus a. Yes, we can calculate average velocity, which we will, as well as instantaneous velocity. Remember that they're two different things. It's the car driving down the road. What's your average speed that you've driven? And what's your speed at the instant when the police officer clocks you? Two different ideas. So we start with the idea of what is particle motion. It's a particle or object moving along a line. It seems kind of funny to call it a particle, but that's what they call it, a particle. It's an object in most cases that we're going to be thinking about in class. So we'll start with the basic concept. Position function is the first thing that's listed on here. So the position function is given by notation as s or s of t. That's always going to represent the position function. The other way I've seen it on some of the problems we'll look at in terms of AP is x of t. So I'll write that over here. X of t or s of t. Our position function notation. Displacement is very simple. Displacement is just the amount of time, over time, where the object is. Where is it displaced? So to figure that out, so my example is s of t equals t squared minus 3t plus 2. That's the position function that we would be looking at. During the first 5 seconds, we're looking for its displacement. So in other words, where is it over the first 5 seconds, or how far did it go? So we take s of 5 minus s of 0. We always assume on these that in s otherwise given, the initial value is at 0. And then calculate it out. So how do we get the 12 minus 2? You plug in the 5 into the t squared minus 3t plus 2. Then you plug in 0 into t squared minus 3t plus 2. And that'll give you the 12 minus the 2, which is equal to 10. Notice that we're going to start putting units on things. Units become very important in these application problems. So 10 meters is its displacement during the first 5 seconds. Will that change if I ask you to find it during the first 10 seconds? Yes, obviously. Because you're going to be plugging, in that case, you'd plug in 10 for t into the position function right here. I'm looking at position function. Minus s of 0, and you get a different value. So it depends on how long we're looking at the time frame of as to what our answer is. Our next big thing we look at is average velocity. I'll go through real basic topics of what we're going to be studying with particle motion. It's going to be very specific as to which things we'll look at in here. Average velocity is displacement over travel time. Notice that we use the calculus notation for what looks like slope because that's all it is. What we learned this as way back when was f of b minus f of a over b minus a. And this was to find the average rate of change. Now we're finding an application of that average velocity. It's the same exact idea. In this case, we'll take the function, which is the S or F function they call it, same idea, S or F, because S equals F in this case. So we would have the S of 5, I'll write it over here, S of 5 minus S of 0 over 5 minus 0. We already know what the top piece is. That was given in the last example. That's displacement. That's 10 over 5. So you can see that written right here, 10 over 5, so it would equal 2 meters per second. Yes, you need to have labels. Average velocity or instantaneous velocity will be a time frame with some kind of, like usually meters. So meters per second. It might be feet per second. Usually it's meters per second. We usually use metric in particle motion. Instantaneous velocity is the derivative of the position function. Now we have to keep straight what's what. Position derivative is instantaneous velocity. Average velocity, again, is just taking your secant slope idea, your S of, or F of B minus F of A over B minus A. Instantaneous is the derivative. If we go back to the function that we were just looking at, here we go. Let's find the derivative of the position function. What is its derivative? These are very simple derivatives to find if you're working with a basic polynomial function. If you're not, oftentimes we will have, again, a very simple function, whether it's sine, cosine, whatever it is. What is the derivative?
This is counter second hour study hall.
Right. What's the derivative? What's the derivative of your function, the position function? Your t is like an x. What's its derivative? 2t. What is it? Minus 3? Okay. So that's your velocity function. Velocity is the derivative of the position function. That's it. Very simple. Find the velocity when t equals 4. Plug in 4. What's the velocity? 5 what? Thank you, meters per second. Just two different things. If they say velocity in the problem, you automatically have to assume it's instantaneous velocity. If it's average velocity, it will say average velocity. If it just says velocity, it's instantaneous. Keep that in your head so that you're not confused about which one is which. This is simply just finding the derivative of the function. Here are some things to write down that aren't in your textbook that will help you significantly when you're solving problems. We're going to be working the next 2 days on some problems from some packets that I developed for the class. And here are some things that will help you. Velocity tells us how fast an object is moving and the direction of motion. We can have a negative or positive velocity. The concept is that if you had a negative velocity, it would be the idea of driving backwards down the road. Now, do we drive backwards down the highway? Hope not, right? But positive velocity is driving forward, so direction. You can be moving up, down, right, left. Basic idea or premise of this is when velocity is positive, that you're moving either up or to the right. When velocity is negative, you're either moving down or to the left. I have on here some other notes for you to write down. When an object is moving forward or the position function S is increasing, the velocity is positive. When an object is moving backward or S is decreasing, so this would be position function decreasing in other words, the velocity is negative. Okay, so we talk about, depends on the situation, things moving forward or backward or things moving right or left, up or down. The highest point then is where the velocity function is 0. The highest point meaning the highest point on the position function. Think about the logic of this problem. In a position function, the highest point, what's the slope at a maximum? If this is my position function, what's the slope up here? Correct, 0. A maximum or minimum has a slope of 0. So that should make sense that the velocity, which is its slope or derivative of the position function, is 0 when the particle is at its highest point. Similarly, that'll happen when the particle is at the lowest point, is whenever you have a maximum or minimum on the position function, you'll have a slope of 0. Next thing we need to know is about speed. How fast are we driving? 30 miles per hour is the speed at which we're going. Speed is just simply, in terms of particle motion, the absolute value of velocity. That's it. So there's two ways we can write it. It's the absolute value of velocity. So that would be just notation, absolute value v of t. Or you can write it in regard to position, which, remember, the velocity is the derivative, first derivative of the position function. So the absolute value ds dt, derivative of s over dt. The next part's extremely important, everyone. You'll be asked this when we look at the packet 2. This week, almost every question, part of every question, is going to ask you about the speed of the object. Speed is increasing when acceleration and velocity are both positive or both negative. Here's the general concept. If you are driving down the road in a forward direction and you hit the accelerator, what happens? What happens? Yeah, you speed up, right? What happens when you let go of the accelerator? You slow down. So if I'm going in a positive direction and I hit the accelerator, I'm going to speed up. When my velocity and acceleration are both positive, I speed up. If I am going forward and I let go of the accelerator, so when one is positive and the other value is negative, I'm going to slow down, so my speed will decrease. Does that make sense? The logic of it is thinking about what happens if you're driving down the road, because that's a simple way to understand what happens when this occurs. So oftentimes we simply say speed is increasing when acceleration and velocity are both positive or both negative. You look at the signs of the answers. That's all there is to this. Look to see at that particular moment, are both of them positive or are both of them negative? In that case, you're going to speed up. Otherwise, if one's positive and one's negative, you slow down. Acceleration. Acceleration is the second derivative of the position function. So our order goes position, first derivative is instantaneous velocity, second derivative is acceleration. So acceleration is the derivative of velocity with respect to time. We note it as a of t. So a of t is equal to dv dt, derivative of velocity, or the second derivative of the position, d squared s over dt squared. Notice on here again we have the two notations, and a of t is primarily going to be used then for acceleration. So we have s or x of t for position, v of t is instantaneous velocity, and a of t stands for acceleration. Now we have an actual meaning for a second derivative. It's acceleration. It's the rate at which you are increasing or decreasing. It's like the rate of the rate idea. So it's the rate at which the velocity changes is what acceleration is, a simple way to understand it. It measures how quickly an object picks up or loses speed. Because remember that the absolute value of velocity is speed. Speed is just not looking and paying attention to the direction of your velocity. That's why we don't say that you're going a negative 50 miles per hour if you're driving backwards down the highway. Speed is relative to, it's always positive and relative to velocity. It's just looking at always the positive portion of it. That's it. So let's go back to our problem. Find the acceleration when t is equal to 4. Our first derivative, we're going to find our second derivative now. Our first derivative was 2t minus 3. So what's our next derivative, or the derivative of 2t minus 3? 2. Does it matter if there's no t in the problem? What does that mean? Yeah, it's always 2. If I get an answer with a t in it, now I can plug in 4. I don't need to plug in 4 here because the acceleration is always at 2 meters per second squared. Notice the units. Acceleration, I always think of second derivative goes with the 2 here. First derivative would be meters per second to the first. Second derivative, meters per second, seconds to the second. I just think that's an easy way for people to remember how to do the labeling on the problems. Questions? Next part we look at is when the particle changes direction. So far, what have we looked at? Displacement, average velocity, instantaneous velocity, speed, and acceleration of this particular object that we started with in the beginning, s of t. A particle changes direction when the velocity, which is the derivative of position, is equal to 0. Why? Because think about the logic again. When the velocity equals 0 is where you're going from increasing to decreasing or decreasing to increasing on a position function graph. So that would be where you have a minimum or a maximum on a position graph is where the derivative or slope is equal to 0. That's derivative is our velocity in this case. So we're going to find where the velocity equals 0. What was our velocity function again that we're working with in this problem? Tell me the velocity function. What was it?
5 meters per second.
No, not answer, just the function, not the value. What was the function for the velocity? 2t minus 3. So we want to know where this equals 0. Because that's where the particle has stopped and changed direction. I go from positive velocity, I'm increasing now, I stop, change direction, now I'm decreasing, for example. So that's where this is going to change direction. It's essentially when it's 0 where the particle stops and changes. Let's solve for t. So at 3/2 or 1.5 seconds is where the particle changes direction. Last part of the problem says, where is the particle when s, remember s's position, is a minimum? Why don't you go ahead and graph this? We have the same answer. The 3/2 or 1.5 seconds in this case is where our minimum is on the graph. It will help you if you graph, and it's certainly not anything wrong with taking a look first before you do any work. Graph your function, graph your velocity function, so graph the derivative, and then graph the derivative of that. And if you have the colored screens, you'll be able to tell very easily the difference between the three functions. It should make sense that where your function is decreasing, that you are below the x-axis on the velocity graph because you have a negative velocity. And where your function is increasing, you're going to be above the x-axis on the velocity graph, and where you're hitting the x-axis on the velocity graph is where you have a minimum on the position function. It works exactly the same as we looked at with the function graphs and the derivative graphs. when we had the basic idea of which is the derivative and function graph and which is the, the little cards that we did with the descriptions. Okay, this is something that you'll probably want to make a note of as well, because this will help you with writing equations. Sometimes you're going to be asked to figure out what an equation might look like. And so this is English versus metric units. And what our standard, it's called free fall constant. On your packets, on the note packet I gave, there's several examples that discuss the idea of writing an actual function using the formula. The formula is right on that note sheet that I'll point out to you later. What basic idea is that with the concept is with gravity and what your position function would look like. Or the value with the t squared, in other words. The rest of it's going to be just your initial velocity and velocity at a specific time, perhaps. Because there's gravity on the Earth, we have to take this into consideration whenever we take a look at like a free-falling object. Anything that uses motion, that's why it's called particle motion, uses this idea. Derivatives in economics, I'll briefly just go over this. We're not going to do a lot with the economics, but I just want to show you a different kind of example, which is finding a derivative in economics. Describes what's called marginal cost, which is the rate of change of the cost. So these are economics terms. If you take or have to take an economics course in college, this would be what it would be about. So we have a specific vocabulary for rates of change and derivatives in economics, and they're called marginals. So it says in a manufacturing operation, the cost of production is the function, the number of units produced, function of x. The marginal cost is the rate of change of cost with respect to the level of production. So sometimes we have to figure out marginal cost in a product, in manufacturing, or any kind of business in this case. And that's what they use, derivatives. So again, lots and lots of calculus and derivatives used in an economics college course. Derivative is just the same as we normally think about it. It's the rate of change. So here's an example. Suppose the dollar cost is given of producing X washing machines. The cost is just your function given. Find the marginal cost of producing 100 washing machines. So our marginal cost, we take the derivative and plug in 100. It's that simple. It's a basic idea of what we're doing in terms of solving. It's just showing you a different style of example of where you would use derivatives in terms of an application. The first thing we looked at was area. That's one place. Area changing, that's the circle one. The big one, of course, is the particle motion with velocity, acceleration, position, which is a physics example. And then this is the economics example.